Now it is group 16. Group 16 members, all of you know. The members are oxygen, sulfur, selenium, tellurium, polonium, and the new member livermorium. These are the members of the so-called oxygen family, which is also called chalcogens. It is group 16, also known as chalcogens, known after chalcopyrites. It is derived from the Greek word for brass and point to the association of sulfur and copper minerals related chalcopyrites. That's the name chalcogen coming from. You know, most of the minerals are either oxides or sulfides, and even sulfides, iron pyrites, copper pyrites existing as iron copper pyrites, that is sulfide ores. From there, actually, the name chalcogens is coming. Oxygen family, one of the highly electronegative elements in the periodic table, as oxygen is the second most electronegative element in the periodic table. Let's have a look at some important name of the compounds and all. Of course, it's a relative abundance. Relative abundance also. Oxygen is 46% by mass of Earth crust. Dry air contain approximately 21% oxygen by volume, all of you know. Abundance of sulfur 0.03 to 0.1% and is available as sulfates. Gypsum, learned in the 11th standard topic, gypsum, calcium sulfate, dihydrate. Epsom salt, magnesium sulfate, heptahydrate. Barite, barium sulfate, also called barium meal, barite. Galena, lead sulfide, galena. Zinc blende, also called sphalerite, zinc sulfide. Copper iron pyrites, copper pyrites. These are some names which we must remember. I don't have to tell you. You are aware of the name of the minerals and their formula. That can essentially come as a direct or indirect question in various competitive examinations. So learning about the name and formula of various minerals and compounds, very important. Livermorium, Lv, that is the synthetic element 116, atomic number 116. Very short half-life, a small fraction of 1 second. Very small fraction of 1 second. Let's have a look at the atomic and physical properties of oxygen family in detail. Atomic and physical properties. Once again, if you look at the electronic configuration, these two will maintain the regular trend 2s2 2p4, 3s2 3p4, while here there will be 3d10, d10 configuration. Here also we have 4d10 and polonium having f14 5d10, means it can reflect inert pair effect. 6s2 electron can involve in inert pair effect. I mean, having a reluctance to take part in chemical bonding. So it can happen, but we don't care much as it is on the 16th group. Of course, there can be, but polonium, radioactive species, we don't discuss much onto the chemistry aspect. Covalent radius, a gradual increase. 66, 104, increasing down the group. Ionic radius, increasing down the group, and all of them form anion. You can see the covalent radius, ionic radius. Ionic radius is greater because it is anion. And this is an important property, electron gain enthalpy. Electron gain enthalpy, it's quite usual, and discussed in the 11th standard topic also regarding the speciality of oxygen. Oxygen, even though second most electronegative element in the periodic table coming after fluorine, the negative electron gain enthalpy is not that much. It is greater for sulfur. Sulfur having high negative electron gain enthalpy. Oxygen coming not even in the second place. Highest is sulfur, then it is selenium, then it is tellurium, then it is polonium, and oxygen is only last, minus 141, due to small size and interelectronic repulsion. So what is the order of negative electron gain enthalpy? Sulfur maximum. Then regular trend down the group. Oxygen coming last. Okay. And discussing about ionization enthalpy, already we have seen the value for oxygen less than that of nitrogen, because nitrogen having P3 configuration, extra stability due to half-filled electronic configuration, that is reflecting in the first three members, probably not in the last member. So whether you take oxygen, nitrogen, whether you take sulfur, phosphorus, whether you take selenium, antimony, you can see arsenic, you can see this is reflecting. For nitrogen family, ionization enthalpy will be slightly greater due to half-filled electronic configuration. However, that is not observed for the heavy members down the group. Electronegativity. Oxygen is the second most electronegative element after fluorine, having Pauling scale value 4. This is having 3.5, and electronegativity decreases down the group. Then density, melting point, boiling point, that also you can have a look at, and is quite interesting to see that whether melting point or boiling point, when you compare with the sulfur and oxygen, if you compare with oxygen and sulfur, oxygen having very low value because it is a diatomic gaseous molecule, while sulfur is polyatomic and solid state. That is the difference. Oxidation state. So oxygen having -2, -1, 1, 2. 1 and 2 with whom? With whom oxygen can show positive oxidation state? None other than fluorine. With the fluorine, oxygen can show positive oxidation state, not in other cases. While sulfur -2 to +6, -2 to +6, -2 to +6, here 2 and 4 only, no -2, no +6. No -2 because down the group metallic character increases. No +6 because inert pair effect. No -2 for polonium because metallic character increases. No +6 because inert pair effect. Is it clear? Right. You can very well notice oxygen showing +1, +2 state in OF2 and O2F2. OF2 and O2F2. OF2 isostructural with water. OF2 isostructural with water. This is OF2 structure. FOF. This is OF2 structure, and O2F2. It is isostructural with hydrogen peroxide. It will be like this, non-planar structure. O2F2 structure, non-planar structure. So that's about electronic configuration, atomic ionic radii, ionization enthalpy, electron gain enthalpy, electronegativity. Now physical properties. Physical properties. There are some important points in the physical properties of group 16. All of us know oxygen, sulfur are non-metals. Oxygen, sulfur are non-metals, while selenium, tellurium are metalloids, semi-metals. Polonium is a metal. Polonium is radioactive and short half-life, 13.8 days. What is meant by half-life? All of you know what is meant by half-life? Time taken for 50% conversion. That is called a half-life. Okay. All these elements exhibit allotropy. All these elements exhibit allotropy. You know what is meant by allotropy. A large difference between melting and boiling point of oxygen and sulfur may be explained on the basis of their atomicity. Oxygen is diatomic gas, while sulfur is polyatomic solid. Sulfur is polyatomic solid. That is the point. On to chemical trend and oxidation state. On to chemical trend and oxidation state. General oxidation state is -2, but the stability of -2 state decreases down the group. As everyone know, down the group metallic character increases, the stability of -2 oxidation state decreases. Polonium hardly shows -2 oxidation state as it is a metal. Sulfur, selenium, tellurium usually show +4 oxidation state also. The stability of +6 state, the stability of +6 state decreases. Inert pair effect, inert pair effect. The bonding in +4, +6 are basically covalent bond. General facts only. All these are general facts only. Now on to anomalous behavior of oxygen. Like every first member, oxygen is also the first member showing anomalous behavior due to small size and all other property related to small size, like high ionization enthalpy, high electronegativity, etc. And regarding oxygen, there is something special. It is able to make, say for example, when you compare H2O and H2S, when you compare H2O and H2S, in H2O, due to the high electronegativity of oxygen, there is strong hydrogen bonding, while in H2S, there is not hydrogen bonding present. Like this, so many abnormal characters we can find pertaining to the very small size and all property related to small size. What are the property related to small size? None other than, electronegativity, high ionization enthalpy, high electronegativity, etc. The absence of d orbital in oxygen, the absence of d orbital in oxygen makes it maximum covalency limited to 4. Basically, such a discussion is not applicable to oxygen. Oxygen rarely exceed 2. Maximum it can have 3, not 4. Anyway, the limit is 4 because it doesn't have vacant d orbital, and that is applicable to all the first members: beryllium, boron, carbon, nitrogen, oxygen. For all these members, it is uniquely applicable. They belong to second period. Their valence shell is n equal to 2. And n equal to 2, they can have only 4 orbitals, 2s, 1 orbital, and 2p, 3 orbitals. That is the limit they can have. In practice, rarely exceeds 2. In practice, rarely exceeds 2. And this is a topic already discussed in detail. Hydrides, we had a detailed talk along with the group 15. That is, hope you remember table 7.2, 7.7 and table 7.9. We had a, inclusive discussion of the hydrides from 3. This is table 7.7. This is table 7.7 and 7.2. Table from hydrides of nitrogen family, and along with the 7.9, table 7.9, that is hydrides of halogens. We are discussing all together, right? Hope you remember the thermal stability, acidic character, bond angle, bond length, various points related to the hydrides, acidic nature, reducing property, etc. Bond dissociation enthalpy, right? Stability, everything. Reducing property down the group, all the property concerned to hydrides of group 15, 16, 17. We are discussing all together already. All these points came for discussion. You can just review. Next is reactivity with oxygen. Reactivity with oxygen. All these form the oxides of the type EO2 and EO3 type. EO2, EO3, SO2 and SO3, like that. EO2, EO3. SO2 is a gas while SeO2 is a solid. In fact, ozone belongs to EO2 type. You see, this is an important point. Reducing property of dioxide decreases from SO2 to TeO2. SO2 is reducing in nature while TeO2 is oxidizing agent. Very important points. SO2 is reducing in nature, TeO2 is oxidizing in nature. Besides EO2 type, there is EO3, SO3, SeO3, TeO3, etc. They are all acidic in nature. They are all acidic in nature. Which is more acidic, SO2 or SO3? Which is more acidic? Both are acidic. Both are acidic. Which is more acidic, SO2 or SO3? It is SO3. Greater the oxidation number, greater the acidic character. So SO3 will be more acidic than SO2. SO3 will be more acidic than SO2. It in fact depends on the oxidation number. Greater the oxidation number, greater the acidic character. Okay. Next is reactivity towards halogen. Reactivity towards halogen. That is the next point. Reactivity towards halogen. There are basically a few types of halides are formed. EX6, EX6, example SF6, sulfur hexafluoride. EX4, example SF4, sulfur tetrafluoride. EX2, example SF2 or SEF2, like that, right? There can be mainly three types: SF6 or EX6, EX4, EX2. Three types we can encounter, and the stability of halides decreases in this order. Fluorides are most stable, iodides are least stable. Multiple reasons, steric and thermodynamic reasons. Steric as well as thermodynamic reason. What is the cause of steric reason? Iodine, large atom, will create steric hindrance, while fluorine, small atom, there will be less steric hindrance, rather it may give steric protection. Iodine is larger atom, it doesn't give steric protection, rather it creates a steric instabilization. Of course, thermodynamic reason, bond strength. Among hexahalides, hexafluorides are only stable. Among hexahalides, hexafluorides are only stable. They are all gaseous nature. They have octahedral structure and they will have sp3d2 hybridization. Octahedral structure and sp3d2 hybridization. Sulfur hexafluoride, exceptionally stable due to steric reasons. All of you know regarding SF6. This is the SF6 molecule. This is the SF6 molecule which is exceptionally stable. SF6 molecule, this is exceptionally stable due to steric reasons. Here actually the small fluorine is creating a steric protection. That is the point here. Normally steric reasons will be destabilization. Here small fluorine is creating a steric protection. and it is sp3d2 hybridization, octahedral in nature. Okay. sp3d2 octahedral in character. Octahedral in character. Among tetrafluorides, SF4 is a gas, SeF4 liquid, TeF4 solid. They have sp3d hybridization. For example, SF4. How SF4 coming is? It is sp3d hybridization. How it is maintaining sp3 hybridization? Yes, 1, 2, 3, 4, 5, like that. And it is SF4 will maintain one fluorine here, one fluorine here, one fluorine here, and one fluorine here, and a lone pair here. I am sure all of you understand what the geometry is. This is trigonal bipyramidal geometry, and the shape of the molecule is seesaw shape. This is seesaw shape. How it is seesaw shape? This is the seesaw shape. Seesaw shape with a lone pair here that maintain seesaw shape. So the hybridization is sp3d hybridization. Electronic arrangement is trigonal bipyramidal arrangement, and shape of the molecule is seesaw shape. All elements except oxygen form dichloride and dibromide. These are all sp3 hybridized about dichlorides. They have tetrahedral geometry. Many of the monochlorides are dimeric in nature. You can see S2F2, dimeric, S2Cl2, S2Br2, Se2Cl2, Se2Br2. These are all dimeric halides, and they undergo disproportionation. They undergo easy disproportionation reaction. Please see what is happening. The way in disproportionation it undergo. This is selenium plus 1 oxidized to selenium plus 4 and reduced to 0. So oxidized to plus 4 and reduced to 0. Disproportionation reaction. So monochlorides undergo disproportionation reaction. Right? So that is about the general characteristics of the atomic and physical properties and general characteristics of the oxygen family. You see a question, H2O liquid, H2S is a gas. Why H2O liquid, H2S is a gas? And the interesting point is, molar mass for H2O-S is very high. This is molar mass 18 unit. This is molar mass 32 plus 2, 34 units. Even though the molar mass is greater for hydrogen sulfide, it is a gas, and H2O is a liquid, even though the molar mass is very low comparatively. See, molar mass is an important factor deciding the molecular attraction. So if H2S is a gas, definitely H2O also should have been gas. It is not. It is in the liquid state. Due to all of you know, that is something special regarding the molecules HF, H2O, ammonia. They are capable of making hydrogen bonding. H2O makes extensive hydrogen bonding, due to which it is in the liquid state. Now our discussion is in detail about dioxygen. Dioxygen in detail. Dioxygen. Let's have a look at dioxygen. First of all, preparation of dioxygen in the laboratory method. Preparation of dioxygen in the laboratory method. It can be obtained by heating oxygen containing salt, chlorate, nitrate, permanganate. Chlorates, nitrate, permanganate. Upon heating, we get oxygen, which can be the laboratory method of preparation. One reaction given is KClO3 decomposing. KClO3 decomposing, giving KCl, liberating oxygen. An intra-redox reaction, all of you know. Similar reactions can be carried out with the metal nitrate. Metal nitrates on heating, you get oxygen liberated. Permanganate can liberate oxygen, right? Only one reaction written, the rest reaction you can try writing. Metal nitrates, for example, potassium nitrate, sodium nitrate, lithium nitrate heating, you know a difference. A brown colored NO2 gas also will be liberated, right? While sodium nitrate, you get sodium nitrite liberating oxygen, like that. So, metal chlorate, metal nitrate, permanganate. Upon heating, you get oxygen gas liberated. Here, chlorine plus 5 will convert it to -1 reduction reaction, and oxygen -2 converted to oxygen 0 oxidation, right? Next one, thermal decomposition of oxides. Thermal decomposition of oxides of metal low in the electrochemical series, like oxide of silver, mercury, lead, etc. Silver, mercury, lead, etc. undergoing decomposition, oxygen gas will be liberated. Regarding Pb3O4, I think many of you are aware of Pb3O4. What is the actual composition? Pb3O4, it is 2PbO dot PbO2. That is Pb3O4. 2PbO dot PbO2. Actually, this PbO2 is reduced to PbO. So, out of 6 PbO you are getting, only 2 PbO2 is obtained by the reduction process. The rest PbO remain as such. So, you have to think about the redox involved in the reactions also. Many times questions, reactions from inorganic chemistry, organic chemistry even can be taken up for the explanations concerned to conceptual questions concerned to redox reaction and even stoichiometric calculations. Okay, that's it. Next is thermal decomposition of hydrogen peroxide. Hydrogen peroxide, upon decomposition, you can get oxygen gas. Hydrogen peroxide on decomposition, you can get oxygen gas. All of you know. Yet another example for what is happening there. This is an example for what kind of redox? Disproportionation. Oxygen -1 converted to -2 and 0. Oxygen here is -1 converted to -2 reduction and converted to 0 oxidation. Disproportionation reaction. Hydrogen peroxide readily decomposed into water and dioxygen. While on a large scale, you can get oxygen prepared from water or air. Electrolysis of acidulated water, you can get hydrogen at a cathode and oxygen at a anode. By the electrolysis of acid water, you can get hydrogen and oxygen. Oxygen can be obtained. While commercial or industrial dioxygen obtained from air, first removing carbon dioxide, water vapor, and then the remaining gases liquefied fractionally, distilling to give dinitrogen and dioxygen. Both are industrially important. I don't have to tell you the importance of oxygen industrially, and in particular medical field, medical oxygen, it's high demand medical oxygen requirement. All of you know regarding that. Now on to properties of dioxygen. Let's have a look at the properties of dioxygen. It's a non-fact, colorless, odorless gas. Solubility, this is the solubility which is sufficient enough to maintain the aquatic life. Aquatic life requires dissolved oxygen, you know. It is sufficient enough to maintain the aquatic life. The liquefaction temperature 90 Kelvin, while freezing temperature 55 Kelvin. There are 3 stable isotopes: oxygen 16, oxygen 17, and oxygen 18. Right? Oxygen 16, 17, 18. Right? You can think about questions like, considering the isotopic forms, how many molecular oxygen you may get. Please think about it. Considering the isotopic conditions of 3 isotopic conditions, how many dioxygen molecules you may get? Okay, how many water molecules you can get considering the three isotopes of hydrogen and oxygen? Oxygen 3 important isotopes 16, 17, 18, and hydrogen 3 important isotopes protium, deuterium, tritium. Even though the availability may be different, can be a hypothetical question. How many water molecules may be derived considering all isotopes? So that kind of questions can also be read in between the lines of NCERT content as such is given. Molecular O2 is unique being paramagnetic. It is paramagnetic. Hope all of you remember. There are 2 unpaired electrons respectively in pi star 2p x1, pi star 2p y1 learned in MO theory classes. Chemical bonding. Dioxygen directly react with nearly all metals and non-metals except noble metals like gold, platinum, except noble gases. Its combination with other elements is often strongly exothermic because all reactions are combustion reaction. Basically reaction with oxygen will be many reactions, combustion reactions, and it's exothermic reaction, except a few reactions like nitrogen oxygen, which is endothermic in nature, which help to sustain the reaction. However, to initiate the reaction, some external energy is required. That is, burning should be initiated with the flashing point. Okay. You can see the bond dissociation enthalpy of O2. It is close to 500 kilojoule energy, which is of course much less compared to N2. N2 it is 950 range. Here it is 500 range, 493 kilojoule. OO double bond. You see it is reacting with the calcium, reacting with aluminium, phosphorus, carbon, etc. With aluminium, all these reactions are highly exothermic reactions. I am sure you might have heard about the high affinity of oxygen with the aluminium. Aluminium oxide is highly stable. And what is the importance of this reaction? It is important in the metallurgical industry, roasting process. And see the combustion reactions of conventional fuels. This is a very important reaction in contact process, preparation of sulfuric acid. And this is important in the preparation of chlorine gas, oxidation of HCl using cupric chloride, giving chlorine gas. Any important point in the uses? Normal respiration combustion processes used in oxy-acetylene welding. Oxy-acetylene welding, steel industry, oxygen cylinders widely used for the medical purposes, high altitude flying and mountaineering, combustion of fuels, hydrazine in liquid oxygen. What is hydrazine? Maybe you are aware of hydrazine. This is hydrazine NH2, NH2. That is hydrazine with liquid oxygen used as combustion fuel in rockets, giving tremendous thrust in rocket. That is about dioxygen. That is about dioxygen. Now there is a talk on oxides. I think all of you know regarding oxides. There are variety of oxides: acidic oxide, basic oxide, neutral oxide, amphoteric characters, acidic, basic, neutral, amphoteric, mixed oxides, simple oxides. Simple oxides further classified into, as I said, acidic, basic, neutral, amphoteric. So a pretty good information you may get from this area also regarding oxides. Let's have a look at. Most of the metal oxides are basic in nature and non-metal oxides are generally acidic in nature. This is simple oxide and this is mixed oxide. Just now I was commenting about Pb3O4 available as a mixed oxide. It is 2PbO dot Pb2O3, right? While similarly Fe2, Fe3O4 magnetite, that is also a mixed oxide. What is the composition of Fe3O4 magnetite? Composition of Fe3O4, many of you know. This composition is FeO dot Fe2O3. It is ferrous oxide, ferric oxide, ferrous and ferric oxide. That is Fe3O4 magnetite. It is a mixed oxide. They are simple oxides and mixed oxides. Further classification comes as acidic oxide, basic oxide, amphoteric oxides, and even neutral oxides. Neutral oxides. Just to have a look at the oxides like all these. Oxides with the non-metallic characters, oxides with the highly electronegative elements. That means when you go to right hand side of the periodic table, oxides are mostly acidic in nature. Have a look at SO2, Cl2O7, CO2, N2O5. They are all acidic oxides. Why they are called acidic oxides? Have a look at the reaction. SO2 when treated with water, you get sulfurous acid. SO3 when treated with water, you get sulfuric acid. Carbon dioxide when treated with water, you get carbonic acid. N2O5 when treated with water, you get nitric acid. Cl2O7 when treated with water, you get perchloric acid. So that is what acidic oxide. An oxide when treated with water, which acid you are getting, and is very simple to write the reaction. Very simple to write the reaction. I think many of you may be aware of this is +4 state. This is +4 state. Oxidation state remain the same. If you take a SO3 when treated with water, SO3 when treated with water, you are getting sulfuric acid. And what is the logic? Here it is +6. Here it is +6. No change in oxidation number. Mostly you can relate that reaction and remember that reaction in that sense. There is no change in oxidation number. Mostly carbon dioxide, carbonic acid +4, Cl2O7 perchloric acid +7, N2O5 nitric acid +5, like that. That's a general observation. So non-metal oxides are generally acidic in nature. Non-metal oxides are generally acidic in nature, while metal oxides are generally basic in nature. But there are acidic characters also. Metal oxides in the higher oxidation state. Metal oxides in the higher oxidation state can be acidic. Mn2O7, higher oxidation state, acidic. CrO3, +6 oxidation state, acidic. V2O5, highest oxidation state, acidic. So there can be like that also. Metal oxides with the higher oxidation state can turn acidic. Lower oxidation state will be basic. While in between they may show amphoteric character. Okay. These are basic oxides. These are basic oxides. Have a look at calcium hydroxide when treated with water. We get a calcium hydroxide. That's why it is called a basic oxide. So acidic basic oxides. And there is amphoteric character, which all of you know what is amphoteric. And at the same time, there are neutral oxides also. So acidic oxide, basic oxide, both acidic basic, amphoteric oxide, neither acidic nor basic, neutral oxides. Carbon monoxide is neutral oxide. Nitrous oxide is neutral oxide. Nitric oxide is neutral oxide. Like that. So this area from the oxide part is also very important. As you can very well understand, aluminium oxide, typical example for amphoteric nature, which can react with acid and alkali giving product. And that clearly indicates the amphoteric nature of aluminium oxide. When it is treated with a strong acid, it acts as a base. When treated with the bases, it acts as an acid, like that. Amphoteric nature. While there are neither acidic nor basic, which are called neutral oxides. These are all neutral oxides. That is a talk regarding oxides. So our discussion was on dioxygen in detail and oxides. What are the oxides? Simple oxide, mixer oxide, acidic oxide, basic oxide, amphoteric oxide, neutral oxide. Right? It will be better you prepare a tabulated arrangement considering all these examples and try to consolidate from the different chapters. And if you go through that area frequently, or periodically. Definitely 2-3 questions you will be able to get for any examinations directly or indirectly regarding the nature of oxides. Okay. Next is an allotropic form of oxygen, ozone. That is next. Ozone is nothing but allotropic form of oxygen. It is too reactive to remain in the atmosphere in the sea level at a height about 20 kilometers. It is formed from atmospheric oxygen in presence of sunlight. This ozone layer protect Earth from UV radiations. All are non-factors learned from the lower classes itself. How to prepare ozone? When a slow dry stream of oxygen passed through silent electric discharge. Normally electric discharge is somewhat violent. It should be silent electric discharge because ozone is unstable and it may decompose. We will get a conversion of oxygen to ozone. 10% conversion occurs and is called ozonized oxygen. This is the reaction. You can see the nature of the thermodynamic nature of the reaction. Formation of ozone is endothermic process. So not a favorable reaction. And ozone is not that much stable. Since formation of ozone from oxygen is an endothermic process, it is necessary to use a silent electrical discharge in preparation to prevent its decomposition. Otherwise, it may decompose back. If concentration of ozone greater than 10% required, you can make use of a battery ozonizer. And pure ozone, boiling point 101.1 Kelvin, slightly greater than water. No, it is in Kelvin scale. Kelvin scale, boiling point of ozone, much below the normal conditions of temperature. Somewhat how much it is? Minus 160, 173 degrees Celsius or so, right? Minus 173 degrees Celsius or so, where it can be, the boiling point is available. It is condensed in a vessel surrounded by liquid oxygen. So it is always comfortable to be there in equilibrium with the oxygen. Ozone-oxygen equilibrium maintenance will maintain the existence of ozone comfortably. Okay. That is about preparation details of ozone if you want in the laboratory conditions. And coming to the properties of ozone, it is a pale blue gas, dark blue solid if solidified, and a violet black solid. Dark blue liquid, violet black solid. It has got some characteristic smell. And in small concentration, it is harmless. But above the concentration increases 100 ppm and above. It will be difficult. It will be uncomfortable for breathing, resulting in headache and nausea. Right? Ozone is thermodynamically unstable. Already I told you, thermodynamically unstable with respect to oxygen. Since its decomposition result in the liberation of heat. You see O2 converted to O3. Is endothermic. What about decomposition of O3? O3 converted to O2, that is exothermic. So decomposition of ozone is exothermic in nature. Moreover, it involves decrease in what is happening. It is 2O3 converted to 3O2, 2 mole gas converted to 3 mole gas. So there is a increase in entropy. So exothermic means delta H negative and delta S positive. You see, both are favorable for the spontaneity nature. Delta G is equal to delta H minus T delta S. This is negative, this is positive. That means delta G is highly negative. That means the reaction is highly spontaneous. So both thermodynamic energy factor and entropy factor favors the decomposition of ozone. Not quite surprisingly, higher concentration of ozone can be dangerous. It may be dangerously explosive because thermodynamically exothermic decomposition, entropy wise increase in entropy, both are thermodynamically favorable conditions for the reaction to occur, right? These two effects reinforce each other, resulting in the large negative Gibbs energy change. Large negative Gibbs energy change is not really surprising. Therefore, just now I commented, dangerously explosive. Higher concentration of ozone can be dangerous to be handling. Due to the ease with which it liberates a nascent oxygen atom, it can liberate a nascent oxygen atom. O3 liberate O2 plus O. Nascent oxygen is liberated. It acts as a powerful oxidizing agent. Ozone is a very good oxidizing agent as it is able to liberate nascent oxygen. For example, it oxidizes black lead sulfide to white lead sulfate. Black lead sulfide oxidized to white lead sulfate. What is the N factor involved there? N factor means change in oxidation number. What is the change in oxidation number? Sulfur minus 2 changes to sulfur plus 6. What is the N factor? Sulfur sulfide, lead sulfide minus 2 converted to lead sulfate, sulfur plus 6. What is the change in oxidation number? 8. N factor is 8. Okay. Now, iodide is oxidized to iodine. Iodide is oxidized to iodine. Like that. So, ozone can act as a very good oxidizing agent. Now, there is another important point when ozone react with that is estimation of ozone. How ozone can be estimated? Answer is available in this paragraph. When ozone react with the excess of Ki, O3 react with the excess of Ki. So, Ki react with the ozone, you get iodine. Buffered with the borate buffer, iodine is liberated. Iodine is liberated, which can be titrated against a standard solution of sodium thiosulfate, hypo solution. It is titrated with the hypo solution. What is hypo solution? Sodium thiosulfate, Na2S2O3. And that stands a quantitative estimation of ozone. Ozone interacting with the Ki solution. Ki becomes I2. I2 titrated with the sodium thiosulfate, and sodium thiosulfate will be converted to sodium tetrathionate, and this reaction quantitatively can give you a measure of ozone. Estimation of ozone can be done in that way. That paragraph explains the estimation, quantitative estimation of ozone. Okay. Further talking about experiments have shown that nitrogen oxide, particularly nitric oxide, particularly nitrogen monoxide, that means nitric oxide, combine rapidly with ozone. Nitric oxide combine rapidly with ozone and is converted to NO2, liberating oxygen. So it's not it's a non-fact regarding our environmental pollutions that NO released from jet engines. A good quantity of NO may be released from jet engines. So that NO, particularly if it is in the stratospheric region, that NO can act as a potential catalyst or potential component causing the decomposition of ozone. You see, NO released from jet aeroplanes may interact with ozone and ozone is destroyed. So that such reactions also remain very important. Yes. Now coming to the structural details of ozone. Ozone is a bent molecule. Ozone is a bent molecule having two resonating structures. These are the two resonating structures, and the hybrid form of which almost all of you might have seen the hybrid form of this. This is the hybrid form of ozone. Both the bond length are equal. Both the bond length are equal 128 picometer due to resonance hybrid character, and the bond angle is somewhat about 117 degree. Molecular dimensions of ozone is also very important. Angular shape, that is ozone. It is used as a germicide, disinfectant, sterilizing water, bleaching oil, ivory, flour, starch, act as an oxidizing agent in the preparation of potassium permanganate. We are going to discuss the potassium permanganate preparation in the next chapter. This is P block, means D and F block elements. We are preparing, we are learning the preparation techniques of potassium permanganate. There also we can have an idea how ozone is involved, or a good oxidizing agent like ozone involved in the preparation of KMnO4. That also is enlisted here. That is regarding ozone, a talk on ozone. So what all points we have gone through so far? Dioxygen, various types of oxides, and then ozone. Now it is allotropic forms of sulfur. Allotropic forms of sulfur. That is the next point. Allotropic forms of sulfur. Sulfur forms numerous allotropes which yellow rhombic sulfur. We call it as alpha sulfur, rhombic sulfur. Then it is monoclinic beta sulfur. These are the most important allotropic forms. There are many forms: plastic sulfur, colloidal sulfur, many forms are there. The most important ones are alpha beta forms. Alpha form is rhombic in nature, beta form is monoclinic in nature. We are learning in the solid state chemistry regarding the crystal lattice dimensions of rhombic and monoclinic. You may review regarding that. The stable form at room temperature is rhombic sulfur. Rhombic sulfur is stable form, and alpha beta conversion occurs at 369 Kelvin, and that is a transition temperature for the two allotropic forms of sulfur. First of all, rhombic sulfur, that is alpha sulfur. It is somewhat yellow in color. Melting point is 385 Kelvin, specific gravity approximately 2. Rhombic sulfur crystals formed on evaporating solution of rolled sulfur taken in carbon disulfide. It is insoluble in water but dissolved to some extent in organic medium, readily soluble in carbon disulfide. That is about rhombic sulfur, alpha sulfur. Coming to beta form of sulfur, the melting point is again somewhat in the same region and specifically slightly less. It is soluble once again in carbon disulfide. It is prepared by melting rhombic sulfur in a dish and cooling till the crust is formed. 2 holes are made in the crust and remaining liquid poured out. On removing the crust, colorless needle-shaped crystals, monoclinic, triclinic, they are all needle-shaped crystals. You get needle-shaped crystals of beta sulfur formed. It is stable above 369 Kelvin. Stable above 369 Kelvin, below which alpha form will stabilize, and that we call it as transition temperature. That is called a transition temperature. Above 369, beta form stabilizes. Below 369 Kelvin, alpha form stabilizes. They have S8 molecules. It is polyatomic in nature. S8 molecules. They are having puckered crown shape. Puckered ring structure. This is what the molecular dimensions and the structural entity of sulfur in the S8 form. This is S8 form of sulfur. This is S8 form of sulfur. It is puckered ring structure with a bond angle 107 degree and a bond length 204 picometer. While there is S6 form in the different conformations, one chair conformation type you can see, bond angle is slightly lower. Obviously, bond length is slightly greater. See, these comparisons are very important and is very simple to memorize. Bond length, bond angle are related. When the bond angle decreases, bond length will increase. You see, 107, 105, slight decrease in bond angle. 204, 205, slight increase in bond length. When bond angle decreases, that will reflect in bond length. Okay, all of you know that. At elevated temperatures, 1000 Kelvin, S2 is dominant species and paramagnetic like O2. How S2 paramagnetic like O2? How O2 is paramagnetic? O2 is paramagnetic due to the presence of two unpaired electrons in where? The antibonding pi star orbitals, pi star 2px1, pi star 2p1. The same way on a higher energy level, we can see S2 is also paramagnetic as due to the presence of two unpaired electrons present in the pi star orbitals. Okay. That is about the allotropic forms of sulfur. Next is a talk on sulfur dioxide. Sulfur dioxide, SO2. Sulfur dioxide. Sulfur dioxide prepared by the combustion of sulfur directly burning, you can get sulfur dioxide. Or you can get the laboratory sulfur dioxide by treating with a sulfite solution in acid medium. Take a sulfite salt solution and treat with acid medium, you will get SO2 liberated. SO2 gas will be liberated. While industrially, we can get it as a byproduct from roasting operation. From the metallurgical industry, during roasting, SO2 gas will be released. That we can get industrially as a byproduct, which can be used for contact process. So roasting is an important source of getting SO2. The gas, after drying, liquefied under pressure and stored in steel cylinders. It is a colorless gas, pungent smelling, highly soluble in water, liquefies at room temperature under a pressure of only 2 atm, and when passed through water, you get sulfurous acid. Sulfurous acid, maybe all of you know, it's not a stable one, but their salts are stable. It is not a stable one, but their salts are stable. It reacts readily with the sodium hydroxide solution. Forming sodium sulfate. And excess when reacting, you get sodium hydrogen sulfite. And it's quite interesting to see that their behavior with alkali is similar to carbon dioxide. The way you get a lime water test in carbon dioxide, you can get the same test in sulfur dioxide. So before testing for lime water test, if you are testing carbon dioxide, you have to ensure no sulfur dioxide is present. Sulfur dioxide can give the same type of reaction, the observation like what you find in lime water test with the carbon dioxide. The behavior of SO2 with alkali is similar to carbon dioxide. SO2 can react with the chlorine, you get SO2Cl2, sulfuryl chloride. So it can act as a scavenger for chlorine during chlorination process, during the bleaching operations and all. If you make use of bleaching powder in a closed chamber, imagine excess of chlorine is settled in that room. It is dangerous, not enter that room before it is anti-chlorinated. So SO2 can act as an anti-chlor. It can react with the Cl2. It can react with the Cl2 converted to SO2Cl2. And this is the most popular reaction, preparation of sulfuric acid contact process. In the moist condition, it behaves like a reducing agent. It reduces ferric to ferrous. Ferric is reduced to ferrous, where itself SO2 is oxidized to sulfate. Sulfur dioxide is oxidized to sulfate and permanganate reduced to Mn2+. You can see the structural similarity of SO2 Structural similarity of SO2 with O3. O3 and SO2, similar structure. O3 and SO2, similar structure. Used in refining of petroleum, sugar, bleaching, wool, silk. It used as an anti-clone, disinfectant and preservative. Sulfuric acid, sodium, hydrogen sulfate, etc. Manufacturing of sulfur dioxide. Liquid SO2 used as a solvent, dissolve number of organic, inorganic chemicals. That's about SO2. That is about SO2. So far, what we have discussed in the area, dioxygen, then oxides, dioxygen, oxides, then SO2, allotropic forms of sulfur, SO2. That is what the main points recently discussed. Actually, we are through the group 16. Group 16. First, we had atomic and physical properties and lot many related points we have discussed. Before that, it was group 15. Nitrogen family completed, right? Now on to oxo acids of sulfur. Oxo acids of sulfur. There are variety of oxo acids of sulfur. H2SO3, sulfurous acid, H2S2O3, thiosulfuric acid, like that. Variety of oxo acids are available, and sometimes you see how it is represented. H2SXO6. X stands 2 to 5. X stands 2 to 5. And drawing these structures should be taken as a practice. These two are important acids. One is H2SO5, peroxomonosulfuric acid. H2S2O8, peroxo disulfuric acid. This is peroxo disulfuric acid, and there is no peroxo monosulfuric acid. I will draw the structure. This is peroxo monosulfuric acid. H2SO5. There is a peroxy linkage. This is H2SO5, peroxo monosulfuric acid. Peroxo monosulfuric acid, popular known as Carros acid. Carros acid. There is a peroxy linkage. These two molecules, when condenses, you get this. This is peroxo disulfuric acid, popular called Marshall's acid. Marshall's acid. And there also you can find a peroxy linkage. There is a peroxy linkage. And this is the one, pyrosulfuric acid, oleum. Oleum means basically sulfuric acid. Oleum mixed with water, you get sulfuric acid. That is oleum. This is sulfuric acid, and this is sulfurous acid, which contain a lone pair present. Similarly, you must try drawing as many examples as possible. For example, let us try H2S4O6. I am taking X equal to 4. H2S4O6. How the structure can be drawn? H2S4O6. It is simple logical idea to try the structures. H2S4O6, tetrathionic acid. It is sulfur 1, 2, 3, 4, and again here sulfur 1, 2, 3, 4, like this. 2 sulfurs, right? And it will be SO, SO. There is OH. There is OH. Now hydrogen is over. There is one more oxygen. There is one more oxygen. Now oxygen is over. So 2 hydrogen over, oxygen over, 2 more sulfur. That sulfur you can give like this. There is a persulfide linkage. There is a persulfide linkage. This is the structure of tetrathionic acid. Tetrathio, sodium tetrathionate, very famous salt, right? And finding the oxidation number also. Finding the oxidation number also taught in the classes. This is -2, -4, -5, and this is +5 state. -2 +2, -2 +2, -1 +1. So -2, -4, -5, +5. right? While these two sulfur will be 0 state, this sulfur will also be +5 state, and average will be +5 0 0 divided by 4. You get 10 by 4, that is 2.5 is the average oxidation number. +5 +0 +0 +5 by 4. You get 10 by 4. 2.5 is the average oxidation number, like that. So you must try to draw all the structural features of the different oxo acids of sulfur, along with what is given in the textbook and which is not given in the text. And most important acid among the given is no doubt sulfuric acid. Sulfuric acid is the most important acid from the list. And manufacturing of sulfuric acid, the most important ones, contact process. This is the schematic representation for manufacturing of sulfuric acid, contact process. Let us try to understand what are the different steps involved in contact process. Manufacturing of sulfuric acid by contact process. First, you have a sulfur burner. This is a sulfur burner where sulfur is kept there and is burned in presence of air and is converted to SO2. SO2 quite naturally will be impure SO2 obtained. There will be lot of impurities, including dust particles. And that dust particles are precipitated in a dust precipitator. This is a quaternion precipitator, dust precipitator, electrostatic precipitator, where dust particles can be removed. But still there can be lot of other impurities. Therefore, it is lead to a washing tower. This SO2 with impurity taken through a washing tower where we are giving a spray of water and the entire washable impurities are removed and the wastewater go out. Entire washable impurities are removed from SO2. Now SO2 becomes wet in nature. SO2 becomes wet in nature. Now that wet SO2 is taken to a drying tower. It is taken to a drying tower where we are giving a concentrated sulfuric acid is sprayed. You know, sulfuric acid is a good dehydrating agent. So wet SO2 will be made dry SO2 in this chamber, and dry SO2 is coming out. Now that dry SO2, many times, you know, my dear children, SO2 may be contaminated with arsenic. There will be arsenic impurities present with SO2. And we want to remove it. Why to remove arsenic? Arsenic is a poisonous component. Every poisonous component can act as a catalytic poison. So we need to remove arsenic component. So here we have a arsenic purifier containing gelatinous hydrated ferric oxide. Arsenic, you have learned, a negative salt. Arsenic is a negative salt, and gelatinous hydrated ferric oxide, that is a positive salt. So positive, negative salt interact. Arsenic impurity will be precipitated, and thereby arsenic impurity can be removed. And then the total mixture is heated to activate the molecules and is taken to a catalytic converter, where in the presence of catalyst, SO2 will be converted to SO3. SO2 will be converted to SO3, right? And now that SO3 is pumped into an absorption tower. It is pumped into an absorption tower. In that absorption tower, we are giving a spray of concentrated sulfuric acid, where this SO3 will be absorbed here in a medium like quartz or something, which is giving sufficient easy liquefaction, absorption surface area, where in that surface area it is condensed and absorbed, and you are getting oleum. Oleum is nothing but concentrated sulfuric acid. Oleum mixed with water is concentrated sulfuric acid. Technically, we call it as BOV, brown oil of vitriol. BOV, brown oil of vitriol, as it is brown oil type component. It is oil type in nature. Oil of vitriol, that is another name for sulfuric acid. Sulfuric acid known as oil of vitriol. You get brown oil of vitriol or rectified oil of vitriol, ROV, rectified oil of vitriol. It is nothing but oleum. Oleum means oil type. Oleum means oil type. Is it clear? So what are the procedures involved? In a sulfur burner, SO2 is produced. All the dust particles are removed. All the impurities are washed away. It is made dry. and arsenic impurities are removed here. Upon heating, moved to catalytic chamber where the core reaction happens. Here actually the core reaction happening. SO2 is converted to SO3 and that SO3 absorbed converted to oleum. This is commercial contact process, preparation of sulfuric acid. Is it clear?